Hello everyone, welcome to Rate Expressions video. This is chapter 15 in your textbook and it's within the unit of kinetics. So the objectives are listed right here. There's 4 objectives for this video. I'm hoping that I'll keep it down below 15 minutes, but we'll see how we do. The first objective is to give the correct units to describe the rate of reaction. Right? And so these units are very specific. You have to use very specific units for it. And it's always going to be the change in the concentration of the chemical over the change in time. And this is called the rate expression. So I'll go ahead and write that. This is called the rate expression. Right? And the rate expression is the rate is equal to the change of the chemical concentration over the change in time. And the units that we use for that is always going to be molarity, so big M, over seconds, little s, or you can also write it as moles per liter per second. Those mean the exact same things. So the correct units have to be used to describe the rate of reactions. All right. When you discuss the rate of disappearance of a reactant or the rate of appearance of the product, watch your signs. Reactants will always be negative, products will always be positive. Right, using coefficients to change one rate to another. Respect the stoich, right? Make sure that whatever your stoichiometric coefficients are, that you put it into the fraction form, right? So if you have a 2 for A, put it into 1/2. If you have a 3 for B, put it into 1/3. And a 4 for C, put it into 1/4. All right, so respect the stoich. Make sure you write the correct rate expressions using your stoichiometric coefficients. The last objective, determine the average rate of a reaction as well as the instantaneous rate of a reaction from a graph of concentration versus time. So both of these you're going to use slope to calculate them. Average rate, you're taking into the entire curve, that entire curve into consideration, whereas an instantaneous rate, you're only taking in one specific point in time. Okay. All right, the rate of reaction is always the change in concentration of a species per unit time. Right, it's shown there. And when I was talking about make sure you pay attention to your signs, right? If you appear, you are being created, that means that you have a positive sign. So for P, right here, you are the product, you are appearing, so you have a positive sign when you write your expression. If you are disappearing, you are no longer there, therefore you are getting rid of yourself. So A is the reactant, and so it's disappearing, so it has to be negative, right? And the units are still molarity per second. All right, in showing how this looks in a graph, hydrogen peroxide, H2O2, that is in the blue, it is our reactant, it is decreasing over time, and oxygen is in the red, it is our product, it is increasing over time. So if you leave out hydrogen peroxide, it will eventually just turn into water, and the oxygen will evaporate into the air, right? So it looks something like that. So this is our reactant, it disappears, and then oxygen is one of our products, and it appears. All right, when you write it out, respect the stoich. I'm going to write that, right? Respect the stoich. Always respect the stoich, right? Just because you have hydrogen peroxide disappearing and water and oxygen appearing, that doesn't mean it's a 1-to-1 ratio, right? You have to respect the stoich. Every 2 molecules of hydrogen peroxide creates 2 molecules of water and 1 molecule of oxygen. So you have to respect the stoich, right? So for hydrogen peroxide, you're going to put it over 1/2 and make sure it's negative because it's disappearing, whereas the oxygen only has a ratio of 1, so that one, there's an imaginary 1 here, right? And it's positive. So respect the stoich. Whatever your coefficients are, turn it into a fraction. If it is a reactant, make it negative. If it is a product, make it positive. All right, so for example, the rate of this overall reaction right here is equal to -1/A change in concentration of A divided by the change in time for A, right? And that's also equal to the negative 1b over the change in concentration of B and the change in time. You can keep going on like this. So these are your stoichiometric coefficients. So the rate of disappearance of A, the rate of disappearance of B, the rate of appearance, the rate of appearance of C, and the appearance of D. Right? So you have the change of the concentration of A divided by the change of time. And if you multiply that by A, you get the rate, right? So you get just this by itself. So what I mean by that is the rate of the reaction, the overall rate of the reaction is this right here. And it's equal to all of these things. But say I just wanted to find just the change in concentration of A over time. I didn't care about the overall reaction. I just wanted A. The way you would do that is you set it up. So rate is equal to negative 1A, change in A, over the change in time, right? This A right here, I have to get rid of it because I only want the change of A. I don't want the negative 1A there. So I'm going to go ahead and multiply negative A to both sides of the equation, right? So the negative A cancels out. And what you're left with is just the change of A over the change in time. Right? So we get negative A times the overall rate of the reaction. So that's what I mean when I wrote all of these out right here. All right, let's go ahead and consider this example. So this is one example. We're still dealing with the same exact equation. So hydrogen peroxide yields water and O2. So the rate expression is written on the top right, and it's asking us to find the rate of disappearance for hydrogen peroxide, and it gave us the rate of disappearance of hydrogen peroxide, negative 2.5 times 10 to the 5th molarity per second, and it's asking us to determine the rate of appearance of oxygen. So it's asking us to find the rate of appearance of oxygen. And what that means is it's asking us to find the change in concentration of oxygen divided by the change in time. That's the only thing it's asking us to find for number 1, right? Specifically for oxygen. So we're going to equal that to negative 1/2, which gets pulled from right here, times the change in concentration of O2. And remember, the change in concentration of H2O2, that was this right here, that was what was given. That's equal to this entire thing. Pretend this is like our given. And then the pink that I'm highlighting right here, that's our x, right? So it's that whole fraction. That's our x and our y, essentially. So we're going to plug that in. So negative 2.5 times 10 to the negative 5th molarity per second. So you're essentially dividing this by 2, and that should give you your answer. So go ahead and do that in your calculators, and that will be your answer. All right, the next thing is asking us to find is the general rate of the reaction. So the general rate of this reaction is the rate, right? So that I'll highlight in green. So the rate of this equation, the rate expression, the rate of the entire reaction is right here. And that's equal to this expression, and it's also equal to this expression. So when we're trying to find the rate of the reaction, let's just choose the easiest one, the change of oxygen, because the stoichiometric coefficient is 1. So for every one chemical reaction, we have one oxygen molecule. So the rate of the reaction is the same as the change in concentration of time of oxygen, right? So it's exactly equal. So what you just solved for number 1 also applies to number 2. All right, let's take this example now. So it says consider the following reaction, and we have 3A yields 2B. So for every 3 molecules of A, we get 2 molecules of B. The average rate of appearance of B is given by this expression, and it says to compare the rate of appearance of B and the rate of appearance of A. So what does this mean? Let's write out an expression. So we need to write out our rate expression. So the rate of the entire reaction is equal to -1/3 change in concentration of A over time. And it's also equal to +1/2 change in concentration of B over time. Right? Those are the same, they're proportional. So every 3 A molecules, there's 2 B molecules. Right? And so it's asking us to solve for B, just the change in B. Right? Just this right here. So pretend that this is our X and we need to figure out how to get rid of this 1/2. So the way that we do this, I'm going to go ahead and rewrite this in blue. So we have -1/3 change in A over change of time is equal to 1/2 change of B over the change in time. And so if I just want the change of B over the change of time, I need to get rid of this 1/2. We'll multiply by 2 to both sides. Right? So the 2 cancels out. And so then we're left with the change of B over the change in time is equal to -2/3 the change in concentration of A over the change in time. Right? So our answer for this one would be A. All right, let's look at this one. This one is a pretty simple one. It looks like it won't be, but I promise it is. So it's asking for the rate of formation of P4. It's asking for the rate of disappearance of pH3, the rate of formation of H2, and the general rate of reaction for the entire chemical equation. So the way we do this, the rate of the entire equation is our rate expression. So the rate of the entire equation is equal to -1/4 change in concentration of pH3 over the change in time. And that is also equal to +1/1. You don't have to put that there, right? The 1 is for the coefficient of P4 over the change in time. But that's also equal to +1/6 over the change in concentration of H2 over time. Right? Those are all equal to each other. They're all proportional. For every 4 pH3 molecules, there's 1 P4 and 6 H2 molecules that are made. So make sure you respect the stoic, right? And so the entire overall rate of the reaction is equal to all of this. And so question number 4 is answered. The rate of formation of H2, right here. If we wanted to figure out just H2, just multiply by 6, get rid of it. If we wanted to find the rate of disappearance of pH3, that's this one right here. If we wanted just this section right here, multiply by the -4 to get rid of it. And then P4 is right here. We don't have to do anything to it because it's just 1 to 1. Okay, let's write the relative rates of change in the concentration of products and reactants in this equation. Again, super simple, you guys. So we have the rate of the reaction is equal to -1/2 of NaCl over time. That's also equal to +1/2 of NO over time, and +1 of chlorine over time. There you go. Those are the relative rates of change in concentrations of products and reactants. If you wanted to isolate just NaCl, for example, so just this part right here, multiply by -2. If you want to isolate just this, multiply by +2. And then this one is a 1-to-1 ratio, so whatever this is actually the rate of the reaction as well. Right, so the average reaction rate, right? So rates of chemical reactions, they aren't constant for the entire reaction. Sometimes it speeds up, sometimes it slows down, and that's why we get those curves, right? It's not a linear line. So the average rate of the reaction is calculated by dividing the change in concentration over the time interval of that reaction. So the beginning of the reaction, the rate is faster than the average, and near the end of the reaction, the rate is much slower than the average. So this is a visual graph to help you guys see that. And so you have your average rate, which is the entire thing, and you have your instantaneous rate, which is just a single point in time. So that's the red line right here. The single point in time can be taken by drawing a tangent line to that point, right? So this is a tangent line. And if you take the slope of it, you get the instantaneous rate of change. If you take the entire curve and you take this end point and this initial point, and you take the rise over run, the slope of that, you can get the average rate. So that's that dashed blue line. And if you want the initial rate, so the rate that you just started off with, it's very similar to the instantaneous rate, right? You take a tangent line to that point in time, and you calculate the slope of it, rise over run. So I hope this helped a little bit. I'll make another video with some more examples, but I think I want to keep this video no more than 15 minutes.